In this lesson, we'll look at more definitions in graph theory, starting with planar graphs. Planar graphs are drawn on a flat plane. No edges intersect except at vertices. When we do have graphs with intersecting edges, some of these can be redrawn to become planar. Graph 1 below is not planar. You can see edge AD and CE intersect. Graph 2 is isomorphic to graph 1 and is planar. You can see that none of the edges now intersect. We have the same number of vertices and we have the same number of edges in each diagram. Not all graphs can be redrawn into a planar form. Here's an example of one. You can see here that there are too many edges crossing over. Here in example 1 from your text, we have a go at redrawing this graph in planar form. You can see AC and BD cross over each other. So what we do is we remove one of the edges that's crossing. Here we've removed edge BD. We redraw what's there, and then we redraw BD without an intersection occurring, like this. Now the graph is in planar form. A graph, when we draw it, divides the flat plane it's drawn on into different regions. These regions are called faces. The following graph shows one bound face and one unbound face, sometimes called an infinite face, labelled F1 and F2. This next graph has 3 bound faces and 1 infinite face. 1, 2, 3 bound faces, the infinite face around the outside. Euler discovered a formula that applies to graph theory, and it applies in particular to connected planar graphs. He found that the number of vertices minus the number of edges plus the number of faces equaled 2. In symbolic form, V minus E plus F equals 2. We can verify Euler's formula using a connected planar graph shown here. We count up the number of vertices, which there are 4, so V equals 4. We count the number of edges, 1, 2, 3, 4, 5, 6, E equals 6. And the number of faces, 1, 2, 3 bound faces, and 1 infinite face makes F equal to 4. We quote Euler's formula, V minus E plus F equals 2. Substitute the numbers we just counted, 4 minus 6 plus 4. 4 minus 6 is negative 2. Negative 2 plus 4 is 2. And so we have verified Euler's formula. In the next example, we can also verify Euler's formula. Here we're told that a connected planar graph has 4 vertices and 5 edges, and we have to find the number of faces. Well, we've told V equals 4 and E equals 5. We write down Euler's formula, V minus E plus F equals 2. Substitute the values we know, 4 and 5. 4 minus 5 is negative 1, and negative 1 plus F equals 2. From our work on equations, change the side, change the sign. This negative 1 becomes a plus 1, and F equals 3. So this graph would have 3 faces. There are some more terms we need to learn the definitions for: walks, trails, paths, circuits, and cycles. We'll use some tracks in Sherbrooke Forest near Melbourne to define these. This is up near Ferntree Gully. So using some of these tracks, we can see there's a gate here, a second gate to the park, an old tree, a waterfall, a bridge, and Fern Gully itself. Obviously there's a lot more tracks up there, but we're just using these for an example. A walk is a sequence of successive edges that connects 2 different vertices in a graph. So if we use the forest tracks from before, we can see if we go from G1 to B to F to G2 to T, back to G2 and back to F, that would be an example of a walk. Notice we've covered some of the edges twice here, and we've certainly covered some of the vertices twice as well. A trail is a walk with no repeated edges. Using the forest track again, we could start at gate 1, go to the bridge, go to the fern gully, come back to gate 2, off to the old tree, over to the waterfall, back to the bridge, and back to G2. So you can see that we've never covered the same edge. A path is a walk with no repeated vertices. As a result, there are no repeated edges as well. So again, using the same map, we could start at the gate 1, move up to Fern Gully, come back to the bridge, go through to the waterfall, over to the old tree, and back to gate 2. So you can see there are no repeated edges, and no repeated vertices. A closed trail has a special name. It's where you end and start at the same vertex. So a circuit is a walk with no repeated edges that starts and ends at the same vertex. Using the forest track, here we start at gate 1, go off to Fern Gully, back to the bridge, from the bridge through to the waterfall, from the waterfall to the old tree, to gate 2, back to the bridge, and back to gate 1. So there is no repeated edges, but we did pass through the bridge twice, and that's fine. And finally, a cycle is a walk that has no repeated vertices except the start and end vertex. So this is a closed path, is another way of calling it, and as a result, there are no repeated edges. Using this example, again, we could start at gate 2, go to the bridge, go to the waterfall, go to the old tree, back to gate 2, and we can see that's an example of a cycle. No vertices have been repeated except for the start and end vertice, and no edge has been repeated.